All right. It is a great pleasure today to have Xie Chen from CalTech giving the CMTC seminar. Xie did her PhD at MIT with Ike Chuang and Xiaogang Wen, and then went to Berkeley and has been at CalTech as a professor since 2014. Xie has done a lot of incredibly important work, especially on symmetry-protected topological phases, topological order, and symmetry-enriched topological order, fracton phases, and is going to be telling us about an interesting direction today on fractons and Chern-Simons theory. So thank you, Xie.
Thank you, Danny.
Sorry, and I just wanted to add one other request before we start. If anybody who is willing to keep their camera on during the talk would be willing to do so, be greatly appreciated, just so we have some actual faces and presence. Sorry, go ahead.
Yeah, thank you, Danny, and thank you for having me here. And about the video thing, yeah, that's just my thing, that if I don't see anybody on screen, I don't see any face, then I certainly don't know what I'm talking about. Sorry about that. So yeah, so I have been working on this relatively new topic called fracton for a while. So what I'm going to talk about today is the effort of me and my brilliant collaborators, as you can see on the screen, are trying to apply a old trick, which is called the Chern-Simons theory, to fracton and see what we can learn from it. So of course, there are experts in the audience on fracton, but I know that fracton is a relatively new topic in condensed matter physics, and it's a relatively exotic topic, not very much closely related to experiment. So I'll try to start from more basic stuff. So I'll try to give a brief review about how people usually think about fractal when people say fractal nowadays, what they mean. And I have to I have to say that this word is a made-up word. It was made up to describe a class of model or class of phenomena that we see since a couple years ago, maybe 4 or 5 years ago. And this word was...
I have a question. You said class of models and class of phenomena. Can you mention one phenomenon where fractons actually apply? I have been bothering Mason. He has not been able to tell me any.
Yeah, exactly. I haven't said anything.
But you just said a class of models and a class of phenomena. So I thought maybe you know of a phenomenon where fractons apply.
Right. So fracton is a class of toy models. And the most popular definition people nowadays use is that these models contain point excitations that have some constraint on their motion.
Right. But do you agree that right now we do not know of any phenomena where ideas of fractons must be applied? Or there may be. It's just a question. This is not a challenge. I'm looking for phenomena.
Yeah, it's not experimentally observed. It's not motivated by observation.
No, that's not my question. No, that's not my question. My question is not about experiment. My question is, do you know of phenomena? Phenomena is a well-defined English word. It has meaning, right? Do you know of phenomena in principle where I must use concept of fractons to understand? That's all my question is. I know it has no experimental implications right now, but maybe in the future, are there phenomena where I must use concept of fracton?
I would say yes. I would say that the class of models that I would introduce all have these common property that point excitations somehow have restricted motion, and that leads to a bunch of weird, more observable phenomena. For example, the localization at low energy, or non-trivial scaling of ground state degeneracy, or entanglement entropy. Some of them are more observable than others, are more feasible to experimentally observe than others, but theoretically they're there.
Okay, so what you are saying, they are well-defined predictions, phenomenological predictions, but whether they occur in nature or not, we do not know yet. Is that a correct statement?
Yes, whether
okay.
They
all right, good. All right, we agree. Thank you. Go on.
Okay. Yeah, thank you. Thank you for clarifying that.
Can I just add one comment to that? Sorry. Maybe Xie, you should mention this. I don't know. It just depends how you define fracton. If you define it generously, there are experimental phenomena. So.
Oh, okay. Thank you. Yeah.
You'll probably touch on this.
I don't think, no, not in this talk.
Like what, Mason? I mean.
Well, I mean, you can rephrase the mobility of dislocations and disclinations.
No. My question was more precise than that. I understand that. I'm saying where I must use fractons. All those things I can understand in a totally different language. So I don't need fractons to understand them. Yeah, I understand that dislocation physics can be done with fracton. And maybe one day we'll find out this is such a compact description that this is what we want to use. But we do not really need to use fractons to understand them. Is that correct or am I wrong?
Yeah, I think you're right. In those examples, we don't need.
Okay, all right. I want to learn about fractons, but I'm doing so many things that I do not want to learn about it until I'm forced to. This is the point of this question, not to give trouble.
Yeah, I'm like that for things that I have to learn. But for fractons, I agree with you that some defects, they're having theories that describe their property. But there are other models that don't have a duality to those lattice defects, which we are forced to come up with something new to describe it. But yeah, so I haven't introduced fracton at all. Sorry. So maybe let me start my talk. Well, first of all, I want to thank all my brilliant collaborators. Xie Chen is a student in my group. And Wilbur is also a student in my group, and Xie Chen especially has been leading this project. And I got a lot of help from talking to Meng Cheng, Michael Levin, and John McGreevy, and many other people actually. So I want to thank them before I start. Okay. Right, so I'll try to just start from some most popular examples where people use the word fractal and where people try to start from here and build up a systematic framework of how we try to capture the phenomena and try to understand the physics. So one of the most popular models, of course, not very experimentally feasible. This is a lattice model. This is exactly solvable lattice model. And it came out of the study of, well, some of them, they're like quantum codes. So they're not very realistic materials, but they're lattice model, local lattice model. So in principle, the kind of physics can appear in some condensed matter system. So this is on three-dimensional lattice. So this model is called the X-cube model, and it's on the cubic lattice. And there are degrees of freedom on the edges. And each edge has a qubit. It has a spin 1/2. So these x and z, I write down, they are poly x and poly z operators. And here, what I'm drawing are the Hamiltonian terms. So first Hamiltonian term contains 12 sigma x around the cube. And here, and the remaining 3 are sigma z terms and involve sigma z around the vertex and involves 4 of them at a time. So the nice thing about this model, of course, is that you can check explicitly that all the Hamiltonian terms commute. And that's why we saw it say it's exactly solvable. So ground state, excited states, the whole spectrum can be exactly solved. Okay, so one thing that's very interesting whenever we see an exactly solvable lattice model is to calculate the ground state degeneracy. And when I say this, I'm implying that I put a system on a three-dimensional torus. So I have periodic boundary condition in all x, y, and z 3 directions. And I find the ground state degeneracy to follow a formula like this. So the log of the ground state degeneracy is 2lx plus 2ly plus 2lz minus 3, where lx, ly, and lz are linear size of the model in three directions. So you can see that this is a very big ground state degeneracy. It's exponential in the linear system size, and usually we don't have something like that. Usually, even with topological order, we can have ground state degeneracy that's a constant depending on the topology of the manifold that you put it on. But here, the ground state degeneracy is exponential in system size. But on the other hand, they are stable ground state degeneracy, meaning that whatever local perturbation you add to the model, but making it not exactly solvable, but that doesn't matter because none of the local perturbations is going to lift the ground state degeneracy as long as the perturbation is small enough. Okay. So this is one of the key features of fractal model, that there are gap system where the ground state degeneracy grows exponentially with system size. And then another main feature that people talk about are these excitations. That's the point particle excitation that I've been talking about. So one of the excitation comes from adding energy to these vertex terms. So there is color-coded the red, the green, and the purple vertex. And these vertices can take on extra energy if, let's say, we apply some string operator. For example, if we apply a string of sigma x like this, then we're going to add energy to the red term and the purple term at each end of the string operator. So it's like out of vacuum, you pop out a pair of quasi-particle and they can be separated by the string operator. And you can do similar things in the other two directions, but there's one subtlety here in that if you apply the string X operator in 3 different directions, you're actually making different point excitation. So here I'm showing them the difference in color, and they're violating different Hamiltonian terms. And the consequence of that is when you try to take an excitation, originally moving, let's say, along the X direction, and try to make a turn into a different direction, then the excitation is actually going to turn into a different excitation, and hence something needs to be deposited at the corner. Or another way of saying this is that the excitation actually doesn't want to make a turn, that it's constrained to move along a one-dimensional line, and that it got stuck on the line. So its motion is restricted to be along the one-dimensional submanifold. Okay. So this is one type of point excitation whose motion are restricted, and the other type is associated with this cube excitation, which can be excited by applying operators on a membrane. So for example, if I apply these sigma z operators on the edges sticking out of a rectangle like this, then what end up happening is that the cube terms at the 4 corners will now have higher energy, while all the other terms have lowest energy. Okay, so these 4 points are like point excitation, but because these 4 points, these cube excitation, they're always created 4 at a time. So there's actually no way you can take one of them and just pull it to somewhere else. And that's why we say that these kind of point excitation also have restriction on their motion. Basically, they can't move by themselves. And that's what we call a fracton excitation. So fracton, as a name describing the class of model, is referring to the whole class of model where point excitations have restricted motion. But fracton, once we use it to describe a particular type of excitation, usually means that those point excitations don't move at all. They just get stuck in space by themselves. Okay, so there are composites of either fracton or linear, which have.
May I ask you another question? So all fracton models, by definition, then have a absolute discrete lattice cutoff, meaning any possible field theory ever is already ruled out. Is that correct, or we don't know? So
this is a lattice model, but the next model I'm going to talk about is a field theory model. So
I see. So it doesn't have to be. Okay, continue then. Okay.
Yeah. So for example, if we make a pair of fracton, like this, And then this pair of fractons separated in the z direction can actually move in a two-dimensional plane. And that's what we call a planar. So if we combine quasi-particle with more restricted motion, we might get quasi-particle with less restricted motion. This is just what we observe from the XQ model. And similarly, if we have lineons, we can make a dipole, and then dipole can move in the two-dimensional plane. Of course, it's still restricted motion because it's a three-dimensional model, but the motion is only in a two-dimensional plane. Okay, so that was a model on a lattice and exactly solvable with Pauli operators. But fractons also show up in very different formulation, for example, in so-called tensor gauge theory. So let me try to briefly introduce you to that. So the tensor gauge theory, of course, is based on the version of gauge theory, which is a vector. So we're used to the vector gauge theory where the electric field is a vector, so it has three components. And associated with that, there's Gauss's law, the usual electromagnetism. Gauss's law saying that the divergence of electric field is equal to charge density. And because of that, we know there's a conservation law saying that if you integrate the charge density over all space, then this should be zero or should be a constant, non-changing constant. And this is charge conservation that we know of QED. And of just, pure gauge theory. And then you can imagine that because of this conservation law, if we start from vacuum, what can happen is that we can pop out an electron and a positron out of the vacuum, and that doesn't violate the charge conservation. But once they're popped out, then they can move anywhere without violating the charge conservation requirement. So this is the usual vector gauge theory, which is not a fracton. But if we make as Michael Fractal pointed out, if we make some minor adjustment and make it a tensor gauge theory, then fracton can pop out. Okay. And the adjustment is that simplest version is where we make the gauge field a tensor gauge field. So now the gauge field is not just a vector, but it has two spatial indices being x, y, and z. And the Gauss's law needs to be modified. And now instead of having just one partial, now it has two partial derivatives. So partial I, partial j, eij is equal to charge density. And the conservation law, now there are more conservation laws. Charge conservation is still true, that the total charge is still conserved. But you can see that now, because of this modified Gauss's law, dipole is also conserved. Now, dipole moment in all three directions are conserved quantity. And because of that, the motion of the charges will be very different. For example, out of vacuum, we cannot pop out the electron and positron pair because that pair carries non-trivial dipole moment with it. And the best thing we can do is to pop out a configuration like this with 4 charge plus minus, so that the total charge is 0 and total dipole is also 0. So this is similar to what we see with fractons in the SQ model, that we have to pop out 4 excitations at the same time. And moreover, once they're popped out, you cannot just take one of the charge and move it because that changes the dipole moment. But rather, we have to, for example, take one pair of dipole and move it. Okay, so those are some previous formulations of fracton. You can see that even though the framework is very different, lattice model, field theory, but they share this common property that there are quasi-particle excitations with restricted motion. So that was something very exotic. Usually we don't see in condensed matter. Of course, we have maybe seen it in some context, but it's not something that people are very familiar with. So this became a topic in the condensed matter theory for a couple of years. We have been working very actively on it. And most recently, what we have been doing is to try to use Chern-Simons theory to describe fracton phenomena and to try to see what we can get. And the reason with Chern-Simons theory is that we have been mostly playing with lattice models. And we learn a lot from playing with lattice models, for example, the SQ model and so on and so forth. But exactly solvable lattice model just become incredibly difficult to deal with once the model becomes relatively complicated. So we were hoping that by using field theory tools, we're able to explore more variety of fractal phenomena and see what theoretical framework we can establish to understand what kind of fractal phases there are and how they're related and things like that. But actually, once we started doing that, once we started using Chern-Simons theory to study fracton, we realized that there are things that's not at all contained in exactly solvable model at all. There are phenomena that's basically beyond what we see in exactly solvable model, which makes the whole class of model more exciting and more interesting. So that's what I'll try to tell you about. Right. Okay. So Chern-Simons theory, of course, has been a very useful and very popular tool in condensed matter theory study, especially in the past decades as it applies to topological phenomena. So this is the form of the Lagrangian that people usually write down for Chern-Simons theory. There's a gauge field of A, and so this is a U1 gauge field in 2+1D with 2+1 space-time indices like this. So this is a vector, a normal vector U1 gauge field. And the Chern-Simons term is, of course, this ADA term. And of course, here we are putting in some indices for these A terms, meaning that there can be multiple components for the gauge fields. There can be 2 or 3, and eventually we'll take it to be infinite components of gauge fields. But for now, for 2+1D, there are, let's say, 2 or 4 or 3 or 5 components of these gauge fields. And the gauge fields can have mutual Chern-Simons coupling. And when they have mutual Chern-Simons coupling, the coefficient is given by a matrix, this Kij matrix. And what we know about Chern-Simons theory is, of course, that this has to be a symmetric integer matrix for the whole theory to be well-defined, for the topological term to be well-defined. And this symmetric integer matrix basically captures the main feature of the universal property of, for example, the topological order you're trying to describe in the system. Okay, and then apart from that, of course, we can have the usual Maxwell term just coming from the 2+1D U1 gauge theory and add it together. This gives us the full Maxwell Chern-Simons theory. So this is all well understood. In 2+1D, for example, in the simplest case, if we just have one component of the gauge field, and then the matrix, this matrix basically becomes a number, then there are very nice correspondence understood between what this number is and what kind of topological phenomena we're talking about. For example, if k is equal to 1, this is the integer quantum Hall effect. And if k is equal to 3, this is the fractional quantum Hall effect with a fitting fraction of equal 1/3. And if k is equal to 0 to 2, 0, so if we have two components of the gauge field, and if we have mutual Chern-Simons coupling between the gauge fields, and then this is describing what we call the Z2 gauge theory or toric code. So, well, this is all, of course, very well understood, and the abelian Chern-Simons theory completely describes the class of abelian topological order. So we are trying to build on this understanding and try to extrapolate that into 3+1D and see what kind of fracton phenomena we can get. Okay, so how do we go to 3+1D? So one way to go to 3+1D is to make the gauge field 3+1D, but we didn't choose to do that. Instead, what we choose to do is to keep the gauge fields still to be 2+1D gauge fields, but instead we make the label, this I and J label, these components of the gauge field to go from minus infinity to plus infinity. So basically we have infinite components of these gauge fields in our theory, and then they can have self-Chern-Simons term or mutual Chern-Simons term captured by now an infinite dimensional K-matrix. Okay. Of course, if we want to have a nice description of the theory, we want the K-matrix to have some kind of translation invariance, just so that everything's under control. Okay. So the reason we choose to do that is because we know that in some simple cases, this is indeed describing some sort of fracton phenomena. For example, in the simplest case, let's just take K to be pure diagonal. So this is an infinite dimensional matrix, and the only non-zero entry are on the diagonal being, let's say, 3. Okay, and so each gauge field only coupled to itself, and there are infinite terms like that. And physically, we know what this is describing. This is describing a stack of fractional quantum Hall system, each with nu equal 1/3. Right? There's no coupling between them, and all the layers are gapped. And when they're stacked together, nothing relevant happens. So each layer just being an independent topological order. And this is a kind of a fracton.
Hello, Xie.
Yes.
Sorry, I have a question. This is Shenjie.
Yes, hi.
Does your K-matrix here carry any dimension or length scale?
Right, great question, actually. And so here I'm just extending the index, but eventually I think what you're, this question is about is whether this K-matrix carry locality in the third dimension, right?
Okay.
Because, yeah, so for us, of course, I don't care about exact length scale, but I care about locality. And that's something we struggle about. And we spend a lot of time just to try to understand what kind of K-matrix has locality. And we can safely deal with that. And I'll spend time talking about that. That's a great point.
Yeah. Thank you.
Yeah. So this theory, even though it looks totally trivial, just being a pure stack of fractional quantum Hall, it already shows some fracton feature, right? For example, the ground state degeneracy of the stack is 3 to the power of n, where n is the height, it's the number of layers in the stack, which is exponential in the linear system times. This is similar to what we see in X cube, although in X cube, it's exponential in all 3 directions, but here it's exponential in 1 direction. And then it has point excitations. It has point excitations just because there are quasi-particle in each of the fractional quantum Hall state. And the quasi-particles only move in the XY plane. And that's what we call a planar excitation. Right? So these excitations, of course, they're not like totally stuck, but still they have some kind of restricted motion within this 3-dimensional manifold. And finally, if you take a cylindrical shape out of this model and calculate entanglement entropy, you will see that entanglement entropy, apart from the area law term, there's a subleading term that's linear in the height of Z. And that's just because each layer is a topological system, and each layer is going to contribute a constant of topological entanglement entropy. And then if the cylinder has a height of in the Z direction, it's going to intersect all these layers, so the contribution of topological entanglement entropy will add up and give you a subleading scaling entanglement. And that's also what we see in, let's say, the X cube model, for example. I didn't mention that, but that's also a common feature of fractal model. But of course, this is a rather trivial type of fracton. And if that's all we see, then we don't need a new theory to describe it. But of course, we want to understand if there's anything more non-trivial beyond that. Well, we can play with this formalism. We don't have to stick with a diagonal K-matrix. We can, let's say, make it slightly non-diagonal by populating not just the main diagonal, but the secondary diagonal. For example, we can keep the main diagonal to be 3 and then populate the second diagonal to be 1. In a way, that's the matrix is still symmetric. And everywhere that's empty is all 0. Okay, so only the tridiagonals are populated. And this actually has been studied back in the 90s and 2000s when people were thinking in terms of 3-dimensional fractional quantum Hall system. So people were thinking about this bulk material but with a layer structure. And how this K-matrix can be obtained, people propose, is to start from, let's say, a stack of fractional quantum Hall but with nu equal 1/5 in each layer. And then you can imagine that the electrons in nearest neighbor layers, they have Coulomb repulsion. So even though they're not in the same layer, they'll try to avoid each other. And so in the wave function, you can introduce this mutual polynomial term, mutual zeros, and that will give rise to these off-diagonal ones. So for example, this one would be Zi minus Zj of electrons in neighboring layers. And what was already known at that time in these papers is that this would lead to some very shocking phenomena. For example, at that time, people talk about the accumulation of charge if we try to insert flux in one of the layers. And that, of course, eventually translates into statistics between these fluxes, because the charge flux attachment is the reason we have flux in this fractional quantum Hall system. And what people find is that the statistics looks very weird. So in the limit where there's infinite number of layers, then we can talk about the statistics of flux in layer I and the flux in layer J, and it becomes an irrational number. It becomes a number like this. So there's a square root of 5 minus 3 divided by 2 and raised to the power of the distance between I and J. Okay, so if I and J becomes further apart, this phase factor would decay exponentially, but it's an irrational number, and that's something we don't see in 2-dimensional topological order. In 2-dimensional topological order, in 2 plus 1D topological order, the statistics are always rational number, 1/3 or 1/5. We never see irrational statistics. Another thing we can talk about is what's the ground state degeneracy, or if you have a K-matrix, what's the determinant of the K-matrix? And this turns out to be very interesting as well. And so it's an exponential of something, but again, the base of this exponential becomes an irrational number. Remember that if we only have the diagonal term, then it's 3 to the power of n, which is integer to the power of n. But here we have irrational number to the power of n. Okay. And of course, there are multiple terms, but when n goes to infinity, this is the dominating term. Okay. And then we can ask even more exotic questions. For example, what's the fusion group? Very similar to questions we ask about 2 plus 1D topological order. What's the fusion group? It turns out the fusion group is a tensor product of, is a direct product of 2 subgroups, and each of them is a cyclic group. And the cyclic group has order Fn, where Fn is the nth number in the Fibonacci sequence. So it goes up exponentially, but also in a very weird way. Okay, so one of them has order Fn, the other has order 5Fn. So to understand why this is so shocking, let's just try to compare to what happens in the XQ model. So in the SQ model, remember we also have these plane down excitations. So let's compare the plane down excitation in the XQ model with the plane down excitation in this 131 model, in this K-matrix model. So in the XQ model, the plane downs are generated by string operators like this. For example, we can draw 2 lines of X And this is a linear dipole excitation, or we can have a single Z string, and this will generate, excuse me, a fractal dipole excitation. And then we can ask what's the fusion group of the planar, if we consider it as some kind of 2+1D topological order. What's the fusion group? The fusion group is the tensor product, the direct product of a bunch of Z2 subgroups, because each of the each of the planar has order 2, right? Fused with itself, it will annihilate back to vacuum. So every element has order 2, and then we just have a lot of them. And this is very different from what we just saw, because now there are a lot of generators, but each generator has a very small order. While in the previous case, we see that there are only 2 generators, while each generator has an exponentially large order, which is given by the Fibonacci number. Okay. And then if we talk about statistics, statistics between these planars will be very short-ranged. So if you have, let's say, this Z string operator, it will anti-commute with this X string operator. But if I move this X string operator downward so that they don't touch anymore, then there won't be any statistics, right? So the fractal dipole will have non-trivial pi statistics with the linear dipole only if they're very close to each other. So statistics is exactly short-ranged. While compared to the previous case, where the statistics is, first of all, irrational, and secondly, it decays exponentially. It's never exactly 0. It decays only exponentially with distance. And then finally, if we ask about the ground state degeneracy of the SQ model has a ground state degeneracy of 2 to the 2n. If we only consider the scaling in the Z direction, while in the K-matrix case, it's an irrational number to the power of n. So the K-matrix model is definitely very exotic, but compared to the XQ model, it's also shocking for another reason. For the SQ model, we had a way of sort of understanding what's going on in the model, which is what we call a foliated fracton theory. So let me try to give you a brief introduction of this, what this foliation idea is all about, and then say why this K-matrix model, this generalized Chern-Simons theory, is actually beyond foliation. So we came up with this foliation idea. So this is 2018, yeah, a couple of years ago. And it worked pretty well for all the lattice model, at least the lattice model, the type 1 lattice model that we understand. So we were able to put a lot of the model we see into the framework and understand their relation to each other, and have a better picture of what's going on with at least the gapped lattice fractal model. But the Chern-Simons theory shows us that there are a lot of things beyond. So let me first tell you what this foliation idea is, and then tell you why this K-matrix thing is actually beyond the foliation structure. Okay, so the XQ model, what we noticed about it is that, let's say we want to compare the XQ model on a slightly smaller system size with a slightly bigger system size. So one is Lx times Ly times Lz, and the other is Lx times Ly times Lz plus 1. And usually we don't expect much to change if we just change system size by a little bit, right? For any model, we would expect the global physics to be pretty much the same. But for a fractal model, they're actually different in a pretty dramatic way, because the ground state degeneracy depends on system size, So if we compare the model on two different systems with different system size, the ground state degeneracy will be different. And usually if we're studying topological model, we would say that, oh, these two belong to different phases, because for gap phases, the allowed transformation we can consider is to deform the Hamiltonian without closing gap along a smooth trajectory. And then we say we stay in the same gapped phase. But for the fractal model, even with different system size, they have different ground state degeneracy. So it seems that the conclusion we want to draw is that different system size belong to different phases. But that doesn't make sense, right? Because we know it's just different system size and the bulk physics is totally the same. It's just slightly different boundary conditions. So it doesn't make sense to call the different system size to be in different phase, which means that we want to find a way to connect them. And we want to maybe redefine what we mean by phase. Okay, so this is what we set out to do. So what we realize is that if we compare the model on slightly different system size, they are different, but they're also related in this way. So if for the smaller side, if we insert an extra layer of two-dimensional toric code, a two-dimensional topological order, we just insert it there, decoupled, totally decoupled. And for this composite system, we can now do some smooth deformation. And then we can show that after this smooth deformation, we can map the left-hand side exactly to the right-hand side. Okay. And that means that these two systems, they differ exactly by this two-dimensional toric code. And that makes sense because these two sides, they have different ground state degeneracy, but the difference can be carried by a two-dimensional toric code, which on a two-dimensional torus will have ground state degeneracy of 4. And that exactly accounts for the difference between the two sides. Right. And that helped us a lot in understanding a lot of the exotic features of fractal model. For example, there's an exact exponential scaling of ground state degeneracy, and that becomes something natural to see because we can just reverse the process now from the right-hand side to the left-hand side, and we can see that we can decouple out these two-dimensional toric code. We can decouple out 1 layer, 2 layer, 3 layer, and we can decouple out many, many layers, and all these layers will just add up to contribute to the exponential scaling of ground state degeneracy in the model. And another thing is the finite order of planars, which we mentioned on the previous slides.
Could I ask you a question?
Yes, sure.
I'm trying to connect with something, it's always, if I can connect with something I am familiar with, I understand much better. So you gave this fractional quantum Hall analogy. So in general, of course, in the fractional quantum Hall physics, we can always put additional layers, and we know new fractional quantum Hall state emerges, and you can have an easily a gram matrix or K-matrix description of that. You have to deal with some, as you said, you have to deal with some metrics. But I never thought about that as a three-dimensional generalization. But it seems through this foliation, you are saying that if I take 2D layers, somehow that's a three-dimensional generalization. I mean, is this something different from what you used to do long time ago, 20 years ago, to do, let's say you have a bilayer fractional quantum Hall, for which your colleague Jim Eisenstein did a lot of experiments, nu is equal to 1 fractional quantum Hall. So you have nu half on the average, or you can have the Hall per infinity 3-1 state, and all of them can be studied if you want using K-matrix description. You don't need to, but you can. Should I think of foliation as a generalization of that, or is this something totally different?
So I think you're referring to, in two-dimensional case, we can just add a layer of insulator, trivial insulator, and then...
No, I have two-dimensional layers. And I'm talking about a fractional quantum Hall state, which is composite of these two. I mean, these things exist, right?
Mm-hmm.
Not insulating, insulating layer in between the two, but there could be tunneling, right?
Oh, yeah.
You could have tunneling.
Okay.
And then I can add a third layer, as you gave some example, or a fourth layer, right?
Yeah.
Is that what foliation is? I'm just trying to, since I do not know what foliation is, I didn't read your paper. I'm trying to connect, or is this something totally different?
So this is in 3+1D, and maybe the analogy to 2+1D is where you can add a trivial insulator layer, a trivial, let's say, just non-topological layer. And then in the K-matrix language, you just add a trivial block, and then you can do some transformation to make another K-matrix. So this is like saying that this is the notion of stable equivalence, that you can add something and then do your deformation and then maybe connect things up to these added.
So this is like adding an insulator. Okay, all right, good, thanks.
Right, so usually in two-dimensional or usually in topological order, what we are allowed to add are, let's say, product states or totally trivial insulators. But here we allow the addition of extra two-dimensional topological layers, which is usually not allowed. But this is because we're looking at three-dimensional physics and we want to look at it in a way that mod out all these two-dimensional contributions. Right, so I actually haven't gone to that yet, but this is, I'm trying, so here I'm just saying that just by realizing this connection, we can make sense of a lot of the phenomena we see in X cubed. For example, the planons have finite order, and they have an order 2 actually. And that's because the planons come from the 2D torical layers. They're literally the quasi-particles in these 2D torical layers, and they have order 2 naturally. And then the statistics are short-ranged, that it becomes 0, exactly 0 after a certain distance cutoff. And that's because, again, the planons come from the layers, so they actually only have statistics with things within that layer. And so because of all this, because of all these corollary that we can derive from the foliation structure, we see that the 131 example that I talk about is actually not foliated because the ground state degeneracy scales with some irrational number, the statistics are irrational, and there's not a finite cutoff for the statistics. So all this is pointing to the fact that this is non-foliated, and this is something we haven't seen before in the lattice model. This is just telling us that to consider gapped fracton phenomena, we're missing things if we just focus on exactly solvable lattice model, but rather this Chern-Simons formulation allows us to have a bigger picture. Okay, so I guess, let me see. Okay, so so this is of course not the original motivation that took us to look at the K-matrix. Originally, we were hoping that by looking at this infinite dimensional K-matrix, we can have a better understanding of the foliation structure. Because we want to understand, for example, how can we decide if two topological order are equivalent to each other up to the insertion of some two-dimensional topological order. But so the simplest example we look at, the 131, is not foliated, but on the other hand, the K-matrix is indeed capable of dealing with foliated phenomena as well. For example, this is a case. This is a slightly more complicated case, not totally translation invariant, but translation invariant up to lattice constant of 3. And then this is an example where the system is described is foliated, and you can see that it looks very different from the non-foliated one, because if we take the inverse of the K, which captures the statistics among the planons, it looks very closely concentrated on the diagonal, while if we do the same thing for the 131 model, it looks very different. For the 131 model, the K-matrix looks nice, but if you take the inverse, then the numbers gets populated everywhere, and then they decay. And of course, from what we know, from what I showed previously, we know that the entries never exactly decays to 0, but rather just decays exponentially.
Xie, I have a question.
Yeah.
Did you say that the 131 kind of phenomena that cannot happen in an exactly solvable lattice model?
Yeah, I don't think so.
What's the argument for that?
Because the statistics decay exponentially. It's like a non-zero correlation length. It's not a correlation length, but it's like a non-zero correlation length. I think so.
I see. So it's like a conjecture that this cannot occur in an exactly solvable lattice model.
Yeah. Maybe I need to think more carefully, but I thought that's the case. But at least for the 131, it's chiral. So.
131's chiral, sure. Yeah,
but even for non-chiral one, yeah. Even for, let's say we have 131 and -1, -3, -1. And then I think so. I think, no, not an exactly solved model. Because exactly solved model, we can, let's say, write down the string operator as a. Oh, okay, let me maybe think more carefully and get back to you.
I would like to know what the intuition is. I mean, you're saying the intuition is just that this statistics decays exponentially.
Yeah, that's what, yeah.
I don't have enough intuition regarding that for why that wouldn't give an exactly solvable lattice model. But anyway, maybe we should go ahead.
Okay, yeah, I'll get back to you on that. Oh, right. So for the foliated case, and actually this K-matrix formalism gave us a nice way to figure out the foliation structure. What we can do is to apply the transformation. In the previous case for the XQ model, remember we decoupled a toric code layer out of the three-dimensional bulk. And here we can do that transformation using the K-matrix. So with K-matrix, it's well known that you can apply these SL transformation such that it basically describes the same universal physics, but by reorganizing the gauge fields in certain way. So here we can show that by using this transformation. So here I'm making a block of this transformation. So the transformation is only non-trivial within the block, but identity outside. And if we apply this transformation to the foliated K-matrix, we can see that some of the dimensions decouple from the other ones. So the red block decouple out, and this red block that decouples out is a twisted Z2 cross Z2 two-dimensional gauge theory. So this one is complicated enough that for lattice model, we were not able to do it, but with K-matrix, it's much easier to see what the foliation structure is. So for this model, we apply the smooth transformation and decouple out the Z2 cross Z2 gauge theory. Right. Okay, so I think I'm kind of running out of time, so I may not be able to talk about all the details of something very important which Shunjie asked at the beginning of the talk, which is regarding the locality of the legitimacy of using K-matrix to study fracton. But I'll tell you the conclusion and then tell you what we know and what we don't know, but without going into details of how we exactly establish that. Okay. So basically what we see is that if we use these infinite dimensional K-matrix to try to describe fractal phenomena, we see phenomena beyond exactly solvable models with an asterisk that I'll get back to, Mason. And then and among all the infinite dimensional K-matrix, we see that there are foliated models. And of course, the hope would be that now we can use this K-matrix formalism to identify examples and to calculate their property, meaning that to figure out how the foliation structure go, and if given two K-matrix, how we can figure out if they are related to each other in this foliated way, right? We can add layers on one side, add layers on the other side, and then do some transformation and make them to look the same. And then study, right, this is the third point about study equivalence. up to foliation using the K-matrix formulation. Of course, in 2D, we sometimes also do that. We take K-matrix, we add another block, and then we do some transformation to see if it's equivalent to some other K-matrix. And that mathematically, as I understand, is pretty much solved problem. There's this stable equivalence between K-matrices, and there are quantities you can calculate to tell you which K-matrix is equivalent to which. But now we're extending it to 3D, and we need an extra locality in the 3D, in the third dimension, to be able to do this. And basically, on the previous slide, we required this W transformation to be non-trivial, only within a finite block, but not everywhere. We're not to do things everywhere at the same time, as long as we're considering a local 3D model, and we're considering 3D gap faces. Okay, so I'm trying to say that this is a different mathematical problem compared to 2+1 dimension, and from what I understand by talking to mathematicians, it's not entirely known what the classification would be under this formalism. So it's something to play with and explore. Okay. And then for the non-foliated model, of course, it becomes more exotic, and we're just looking at examples. And so the 131 is one example, but there are other examples, many other examples that, and some of them look even more weird. And we want to calculate their property and understand just starting from the first step, how to interpret their structure. So for the foliated one, we understand, oh, there's foliation structure, and we can define equivalence using that. But for the non-foliated one, we don't even know how to understand the notion of phase for these models, how to understand the renormalization group transformation for these phases, how to compare a model with different size but look totally different, and how to see they're actually the same model. Okay. So these are not done yet. This is just me trying to paint a picture of where we want to go. But this paper I showed you, what we did is to step back and answer Shengjie's question about whether what we're doing is legitimate, like whether these K-matrices are literally representing local 3D model. If they're not, then we may be getting over ourselves, right? And so we want to understand very basic questions of, do they represent local 3D model? And if they do, are these models gapped or gapless? If it's gapped, we're safer. If it's gapless, first we need to understand if it's a stable gapless model, and it's not entirely obvious. And then if it's gapped, we have quasi-particle excitation, and we want to understand what kind of quasi-particle excitation that is. Okay. So yeah, I don't have time to go into the details, but let me give you the answer of that. So these 131 matrix or things similar to that, those things have been studied for 20 years, well, actually 30 years. So this original paper, they study these K-matrix using Laughlin wave function, and that's perfect. And using Laughlin wave function, you can even calculate energetics and get a phase diagram, and great. But we are trying to deal with things. We're trying to talk about equivalence between K-matrices. So we're considering the whole class of K-matrix. So we want to be able to deal with situation where Laughlin wave function doesn't quite work. For example, you have negative entries in Laughlin wave function, or for some other reason, the analogy doesn't work. So we were hoping to just formulate our answer based on K-matrix. And what we get is, what we were able to understand is that for quasi-diagonal K-matrix, meaning that non-zero entries are all within a certain distance from the diagonal. And that's what we call a quasi-diagonal K-matrix. And because K-matrix are integer matrix, so there's no issue of entries decaying. It's just non-zero or zero. So if all the non-zero entries are within a certain distance of the diagonal, we call it quasi-diagonal K-matrix. And for all these K-matrix, we're safe, meaning that we're literally dealing with local three-dimensional models. And what we did to check that is to find a lattice realization of this K-matrix. So maybe this is redundant, but for me, it's a very necessary exercise to actually see everything very explicitly realized on the lattice. Not exactly solvable. Now, this is not an exactly solvable model, but we were able to convince ourselves enough to say that this is actually legitimate. And more importantly, we were able to understand the shape of the string operator, the form of the string operator, which tells us a lot about the planar excitations in the model. And then we can get the spectrum out of the K-matrix from some field theory calculation. So let me just skip all the lattice construction part and just get to the summary. Okay. Am I still sharing my screen?
Not right now.
Oh, okay. Let me reshare it. Sorry. Guess I got out of it. Okay. So let me just get to the summary part. And if you are interested in how we did the lattice construction, I'll be happy to give a maybe 1 minute recap in the question part, in the question and answer part. So to summarize, we were able to give a lattice construction, local three-dimensional lattice construction for all the quasi-local K-matrices. So they're literally legitimate three-dimensional local models. And moreover, we were able to understand to some extent how the quasi-particles are created, and in particular, how they're localized or not localized in three spatial dimensions. And we were able to find out whether it's gapped or gapless. So basically that reduced to, that is of course well understood. So basically get the spectrum of the K-matrix. And that tells you whether it's gapped or gapless. So in 2+1D, whenever we see a K-matrix, unless they're accidental zeros, we always say that it's gapped. But in 3+1D, there's of course this added complexity that the eigenvalues may not be exactly 0, but they might approach 0. So that's a more interesting thing that we need to consider in 3 dimension. So in 3 dimension, when we see that the eigenvalues of the K-matrix approach 0, as K-matrix gets bigger, we know that the system is actually gapless. And we can get examples of gap foliated, gap non-foliated, and gapless theories described by these quasi-local K-matrices. And of course, this is just us setting up the stage to explore what is actually being represented by this theory, right? For example, we can try to come up with conditions for when a K-matrix will describe a gap foliated versus a gap non-foliated theory. We have been making some progress along that line. Basically, Xie Chen is a mathematician in the group, and he did a lot of proof regarding these K-matrices. And then, and if we find foliated ones, we want to understand the equivalence in terms of inserting 2-dimensional layers and then doing some SL transformation, local SL transformation on these infinite dimensional K-matrices. And then for the non-foliated ones, we're still at the stage of just trying to look at examples and see what can happen and try to make sense of things. And finally, the gapless ones is a big open problem. I didn't talk about that at all, but whether the gapless ones is representing some stable gapless phases or there's some instability towards some gapped phases, those things are also very interesting to explore. So I'll just stop here. Thank you.
All right, thank you very much, Xie, for an excellent talk. Let's open up the floor to any more questions at this point.
I have a question. Supposing you restrict your analysis to K matrices with determinant 1, is there any sharper statement that you can make?
No, we actually didn't consider too much about determinant 1, but that may be a good idea just from a mathematical point of view, right? But well, we didn't consider too much because there are no quasi-particles, so not too much to talk about. But that's a good point. Yeah, from a mathematical point of view, maybe we can look at these quasi-diagonal K-matrix with determinant 1. Then I don't know why there's nothing, and maybe maybe just see if we can through this local insertion of non-degenerate K-matrix. I mean determinant 1 K-matrix, and doing local basis transformation, we can map them all to each other. Maybe that would be the first one to see. Yeah, that's a great point. Thank you.
So I had a question. So this 131 K-matrix, you pointed out that you can realize it as like layering nu equals a fifth plus Coulomb interactions. Presumably, since this 131 thing is not foliated, you have to go through a phase transition. You would expect that for the 131 state anyways. But is there as n gets large, is there a nice picture for this phase transition? Is there like a p-string condensation picture or something like that?
No, it's definitely not. Well, definitely nobody talk about it in the sense of p-string condensation. But yeah, I don't remember in those papers back in the 90s or 2000s people talking about this particular transition. But maybe it's somewhere in the literature that I'm not aware of. But that's a good point. That yes, first of all, definitely there's a transition, and what that transition will look like. I think Santil mentioned something to me. We were talking about phase transition in foliated fractal models. I think they were looking at just layers, and then so stack of topological layers, or maybe something like that. And then you can imagine that each layer going through a transition, but close to transition point, then they become coupled, right? And then you can ask whether I think the question they were looking at is whether the coupling is relevant or irrelevant at the transition point. But maybe that's not exactly answering questions. It's just something that come to mind.
Thank you. Are there any other questions? Maybe I can ask one more actually. So you said that these infinite K-matrix models don't, the non-foliated ones don't have an exactly solvable model, but you do have local models for which you can extract a lot of information. What is the basic nature of these local models? Are these frustration-free models? Are they kind of based on the Haldane pseudopotentials, something like that?
Right. Thank you. And yeah, just just very quickly go through this idea. So this is of course what Meng taught me. So this is what we did. We took a stack of integer quantum Hall layers. So each blue line is an integer quantum Hall. And then we assign charges. Well, there are many charges. So each of these A's correspond to one type of U1 symmetry. And the A's are the background gauge potential. And then you can see that the first three layers carry charge under A1. And the layers 3, 4, 5 carry charge under A2, and 5, 6, 7 carry charge under A3. And then you can integrate out the fermions. Integrate out, meaning that you have a Lagrangian where originally you have a bunch of integer quantum Hall, and then you have this coupling to the external gauge field, and then we make the gauge field dynamical. Of course, we make the gauge field dynamical gauge field and then integrate out the fermions. And then you can see the 131 pop out, because here this A1, it couples to 3 integer quantum Hall. So if you measure the self-Hall conductance, it's 3. But if you measure the mutual Hall conductance between A1 and A2, they overlap on a single layer of integer quantum Hall, so there's a contribution of 1. So by playing this trick, you can construct basically any quasi-diagonal K-matrix in this way. So this is the idea of starting from integer quantum Hall and have planar symmetries and then gauge those planar symmetry. But because we started from integer quantum Hall and then we couple to U1 gauge field, so nothing is exactly solvable here. But we think it's safe enough to make the claim.
I see. Okay, thank you. All right, are there any further questions for Xie? All right, if not, let's thank her again for an excellent talk.
Thank you. It's nice to see you.